So tonight I want to see my dude moving. Crazy, I know, right? I want to see my dude walking around. So I click here, the dude from here goes to here. I click here, the dude goes from here to here. Okay. The way to do it, so the way to do it. How do we do it? Good question. Let's check out the app. What? Okay. So if m input, so unit move unit, so input dot get keyboard, no get mouse dot left. Oh, I know, I need to I need to check whether or not the like if the left mouse button just clicked, you know? Do I actually need to do it? Well, not for now. What do I do? So vector lighting data vector 3 vector 3 what's happening? Something strange? Okay, so the problem obviously I never have like time to do things. unit target vector 3. Well, that's it. Unit target, move unit, make the unit follow the target. If input.getMouse.left, what happens? Well, it happens that the unit, so m input dot auto mouse, m input dot get mouse. This get mouse, okay. So const auto mouse. Now dot x dot y. The x and y are the screen coordinates, I presume. Yeah. The client coordinates. So that would be int window x mouse x int window y mouse y. The idea is that I think if I take the camera dot get view matrix auto view wait, direct x math direct x toolkit simple math project, something like that. Maybe viewport. Compute tile, compute display area, projects a 3D point using given world, view, and projection matrices as the viewport, moving from world coordinates to screen. Unproject, reverse projects a 3D point using a given world, view, and projection matrices. So projects a reverse project using given world, view, and projection matrices. World, so I take the up, the projection, the view, and the world. The up, the projection, the view, and the world. World matrix. The view. Describe the position of the viewport. Fantastic. This probably calls, yeah, unproject. I don't know why we need the world. The world of what? The world of what? Let's ask ChatGPT. So, let's use the performs a reverse projection which involves a several matrix to go from screen to world space. Reverse well, this means how objects are positioned in world space. When you need to know how the object is oriented in the world relative to the camera's position. The world matrix ensures for the model's actual position and rotation within the world. Because it contains like reverse the camera transformation in the inverse of the view matrix to get the coordinate in world space. Well, I know what I'm gonna do, so and it's simply the up vector 3 up. What's the, why do you need the up? Well, whatever. Oh no, it's not up. It's the point. Okay. The point, it's the window X, window Y. The screen space point you want to unproject, so the mouse coordinates. The projection is camera.get projection matrix. Camera. What's your problem? The aspect, of course you need it. Well, whatever. Like, I'm YOLOing right now. Camera dot get the view matrix. Get the view matrix and then the world matrix identity, and fuck it. When I pass the viewport 0 0 IX IY IW, I mean Z imxz. When I go to the renderer and I call render, no, yeah, the mean depth is 0, the max depth is 1. So yeah, it's stupid, but my okay, so it's 0 0f 0.0f client width, client height. Okay, now we unproject. Like why the viewport? Like why the viewport? Oops. Why not call the... Oh, because... Are you happy now? Fantastic. Obviously the cube is the cube like let's do 2 just because. Oh yeah, here it is, our beautiful icosphere. I could make it a little bit bigger, like so, I think. Okay. What? I get it now. So view. Yeah. So okay. Basically it's the camera position now. Like these world matrix is used to transform from like our camera position plus orientation, whatever, to our basically like this is just the camera. This basically I got the camera, the position of the camera right now. That's just the position of the camera. What I want is to like move it. Do I want to move it back? Like if I do this, I want to oh no, it's correct. Yes, it's actually correct. It's actually correct. So we got from mouse well, it's always the It's always at the camera position. But I want to cast a ray from my camera. I want to cast a ray from the camera. So what I did is like useless. Of course. I just wasted 30 minutes doing something completely useless. Yes, that's programming for you. Well, fantastic. Problems, solutions and problems and solutions. So at this point, does it even make a difference? Well, does it even make a difference? What? Does it even make a difference to to simply like take the camera position? So Google, help me. How do I cast a ray from camera? With its direction controlled by the mouse. Ray assigned to mouse position. What? When the mouse is at the door, I want to do something. I'm trying to cast a ray, but a ray doesn't hit the door. And I can't find what exactly it is hitting. It is very specific. Yes, I inside this space. I don't know if this is to get the direction. The ray has to travel in. I first create a vector. I then rotate this vector by the rotation of the camera. If you already have the forward, this should give the ray direction, which along. Yeah, but the problem is that I can take the forward and then rotate it. could. Godhood. Oh my god, fantastic. Someone that speaks my language. Let's check if this renderables XML is clicked. Int. I'm present twice to build array from near to far plane. Yes, of course. I'm stupid. Of course, it's so stupid. Why I didn't? I did not think about it. Yes, you can, because it's, oh yes, because it's in. At the start I said, oh, but why do I need the third coordinate? Yes, because it lets you do like, because this is screen space with the z value being from 0 to 1, I suppose. Yes. So yes. So as of right now, let's just pretend 3 PA PB and 255. Okay, and now let's just boom, save, blue, PNG. Now blue, red, ref, no, blue, ref. And the idea is that nope, render unprojected points So PA, no, PAR for red, and PB. So everything red, obviously. So from red, let's say, to blue. Let's see what happens. What? Oh yes. Something was wrong. So what? Where is the blue? Where is the blue? Where is the blue? Where is the blue? Dog. Why not, like, why not? Why not this? This I think it's cool, right? Am I demented? Am I stupid? Like, PRPB. Am I completely delusional? Here is the blue, so here is the red. Always has been. Okay, so this doesn't work. What? Projection. What? Go away. This doesn't work. So this dude is telling me do it yourself. Stupid. Mm-hmm. Mm-hmm. So what happens? I think they get completely ignored. What? There is something. There is something. What? There is actually something. Where is the blue? Where is the blue, dude? Oh my god! Here it is! The red! So it works! I was just trolling. So, wait. Zero. One. pb.normalize. And then so it actually worked. It's me that I'm let's try something like this. So it's from red to blue. So it's something like oh my god! Oh my god! Yes! Yes! Yes, baby! Woo! Okay, sorry guys. So that's what's happening. Beautiful. So this is it. Like do something like this. Do something like this. Something like this. Something like this. Something like this. Perfect. That's really cool. Okay. Okay. So basically what's happening, I think, is exactly this basically. So we take the screen position, we take a point in screen space plus the z value, like with the depth, okay, and so in screen space basically, and we go through this world view projection, but like not from world to view and from view to projection and then from like onwards, but from projection to view to world basically. That's it. That's it. So we are using the inverse of the world, the inverse of the view, the inverse of the projection, and we have our maybe like it's doing something here for the because the projection metrics outputs what? Does it output? Yeah, screen coordinates. Does it output like clip space? Okay, it does, like it's in clip space. So it's basically, let's pull out the Bible. clipping. So projection and then clipping. Projection, we transform which transforms the view volume into a unit cube. Okay, so clipping transforms the view volume. So volume can have a cube is called the canonical view volume. So projection. Let me pull up my notes, which I'm not gonna show you because I can't just show you my notes, but with the real-time rendering so the projection matrix is to transform view to clip space. Clipping, the clip space is designed so that the equations that describe the view volume are as simple as possible. Basically, four inequalities. A primitive that lies fully inside the view volume is passed to the next stage. A primitive that is entirely outside the view volume is discarded. All the primitives that are partially inside the view volume are clipped against the view volume. It is important to point out that clipping produces new vertices. Yes, of course. After all this is done, perspective division is performed. This consists in dividing the clip space x, y, and z coordinates of each vertex by its w coordinate. The perspective divide converts the resulting vertex positions into normalized coordinates. So basically, the projection method is to transform from view space to clip space, and the clip space is something of the sort x must be included between minus w and w, y must be included between minus w and w, and z must be included between minus w, and w usually is greater than 0 for direct 3D, and w must be greater than 0. So the idea is that we have this sort of cube. Okay, we basically have transformed our view volume, the frustum of the camera, which may be like a box projection, like orthographic, or a truncated pyramid for perspective projection. So for perspective projection, and the projection matrix actually squashes space so that the thing is now a cube. Not unit cube, a cube. Okay. Then we perform clipping, and then we get to the normalized device coordinates. Okay, and from the normalized device coordinates, we can get the screen space, the actual screen space coordinates. Okay, normalized device coordinates, yeah, we get the screen space coordinates with a depth that gets discarded or saved to the depth buffer. Okay, so now when I perform clipping in normalized device, like a question that always puzzled me is, why not perform clipping in normalized device coordinates? Why do we do the projection, clip space, do the clipping, and then do the perspective divide? Well, the idea is that the reason why clipping doesn't work well in normalized device coordinates is that the perspective divide moves points behind the viewer to the front. So triangles behind the viewer would not be clipped away correctly as at the front plane. Instead, they would be clipped at the back plane, which obviously is not correct. So yeah, that's it basically. The reason why clipping doesn't work well is that the perspective divide moves. I wrote it myself, I swear. Moves points behind the viewer to the front. Since W contains minus Z, so triangles behind the viewer would not be clipped away correctly at the front plane. Instead, they would be clipped at the back plane, which obviously is not correct. So the idea is that we start from screen space coordinates plus with a depth value. We convert to normalized device coordinates, meaning we convert the screen space x and y, keeping the depth. Supposing we gave like an already normalized depth. Then we well, if we get something in... Oh, the problem is that we don't have the W. Or we simply keep a 1. Okay. So we don't... okay. Why? Well, because if we see it, we know for sure that our x, y, and z values are like between minus W and W. Okay. So can we get the W from the projections? Yeah, not really. Do we? Well, we could. So there is some math, mumbo jumbo, that I don't really care about. How can we do it? Because how can we take this for like, say, 1 y? So we take the z. Why? Ah, okay. This makes way more sense. Like what? Take the 1. the projection. So the idea is that we can simply suppose that we give for granted that that thing is 1. In clip space. But isn't clip space, W between minus W and W? I'm puzzled. So yeah, I have a lot of questions. Well, whatever may be right. Like, why not 1, 2, 3, 4? Does anything actually matter here? Like, why not 10? Mm. 10 is not good. Why not minus 1? That's not good. Probably because they must be between 0 and 1. They must be between 0 and 1. So this is important. Because it's the Z, obviously it's the Z, sorry. Obviously it's the Z. But the W. So the clip space, because that is clip space, okay. Then you simply transform the clip space using the inverse of the projection. But the problem is that the inverse of the projection doesn't... This is clip space, but this is not clip space. This is normalized device coordinates. These are normalized device coordinates. So we skip the perspective, the inverse of the perspective divide, simply because we cannot know. We cannot know, like, whether or not what's W? We cannot know what's W, the W component. So we splash the sorry. No. What? The implementation is beautiful. So we take the vector -1, 1, 0, 0. The scale. Viewport width -0. Viewport max z minus, okay. The reciprocal of the scale. Okay. The offset minus viewport x minus viewport min z, multiply add scale d dot v. What's the v? Oh, okay. Vector multiply add. Goodbye. Should have done that from the start, honestly. Computes the product of the first two vectors added to the third vector. Okay, beautiful. So scale times offset plus this thing right here. This is the offset. The transform, we take the world, the view, and the projection, we take the inverse, perfect, of that. What's V? Oh, we take the point, this times this times the offset, this times this plus the offset, oh, D is this, oh, this, it's the constants. It's the constants. So the scale, the reciprocal, per component reciprocal. Okay, okay, just to make sure. So the reciprocal of this, then we complete the offset. So, to be honest, here the transform, it's just the inverse. We take the projection, sorry, the world view and projection and the inverse. Multiply these three, take the inverse, so perfect here. I'm interested in what we do like before doing that, and I think it's worth it to just like do some hand calculations. So okay, so obviously the pen is cringe, doesn't really work. Okay, this should be alright. Okay, so let's do some, like D is the vector -1, 1, 0, 0. So -1, 1, 0, 0. The scale, let's call it S, is the viewport width times 1/2, clearly, minus the viewport height times 1/2. So viewport width times 1/2 minus viewport height times 1/2. So Z max minus Z min, okay, and 1. Beautiful. The offset, let's call it O. So this is the scale. It's the set. The offset is minus viewport, so viewport X minus viewport Y. Oh yeah, because we also have the X and the Y, of course, minus viewport min Z, so Z min 0. Sorry, the scale is not this, but is the reciprocal of this. So basically the scale would be this is the view width divided by 2. If I take the reciprocal, it would be 1 divided by the view width divided by 2, which is 2 divided by the view width. Okay, so let's write it like this: 2 divided by the view width minus 2 divided by the view height, 1 over Z max minus Z min and 1. This is the scale. Yeah, okay. This is the scale vector. The offset, we start from here and say, so scale reciprocal of the scale. The offset is this thing, and then we do the multiply add. Multiply add, we told, we like got previously. It's just first times second plus third. It's a multiply add. So it's a scale. It would be something like what? Scale times offset. Oops. Scale times offset plus d. So what we want, please, for the love of God, we can better visualize it, I think, if we do something like this. And the D, yeah, much. Let's keep things like Y. So the multiply add would bring something like this: multiply, 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 add, and this thing goes to the offset. So basically the new offset is 2 divided by the view width. So this is basically minus so it's 2, it's minus 2 Vx divided by view width, so it's 2 divided 2 over view width times minus view x, so it's minus 2 Vx, okay, minus 1. Oops, minus 1. This is the same, so it's basically not the same, because this is minus minus, so this is plus. So this is just 2 view y divided the view height, but here we get the plus 1, and we cool, and here it's just the minus 1 over, sorry, z min divided by z max minus z min, plus 0, 1 times 0 is 0. Okay, this is the offset. Now we compute the transform, I don't care about it. The result that we call R, what is the result? The result is a vector multiply add, where we take the V so it would be something like x Y, Z, W. The scale, so the scale plus the offset. Whoops. The new offset though, not the old one. So take it from here. So as before, this is what we need. Y, Z. So this is the V. The scale, the offset, and what we need to do is to get the result. We need to multiply, add, multiply, add, multiply, add, multiply, add, and so we simply say, okay, this is 2 x divided by view width minus 2 vx divided by view width minus 1. This is minus 2 y divided by the view height plus 2 view y plus 1 minus 2y over view height plus 2. Okay, and here we got the z. Oops. Z divided by z min minus z max minus z min divided z max minus z min, and this is the W. Okay, so this V right here is a 0, is a 1, is initialized to 0. Beautiful. So for us this W is 0. So 0 times 1 is 0, plus 0 is 0. Oh, fantastic. So they use the 0 thingy. Now, let's do some simplification. So this is same denominator. So we can like collect the two. I don't know how it's called in English. It's 2, and here is x minus Vx divided by view width minus 1, of course. This is 2 minus y plus I could do something more. Minus 2 y minus view y divided by view height plus 1, and this is z minus z min divided by z max minus z min 0. So this is basically, we're just mapping. So in our scenario, this and these are 0. So in our scenario, so obviously I need to translate the view x. In our scenario, this, which is 0, the z min is 0, the z max is 1. This should simplify things. What is happening? Of course, the viewport. Min depth is 0, max depth is 1. So R is 2 x divided by the view width minus 1 minus 2 y divided by the view height plus 1 z divided by z max, which is 1, minus z min, which is z, so it's just z. Okay, so x divided by the view width this is just mapping the x, because when x, so basically let's take this for example. So 2x divided by view width minus 1. So when x is 0, this means that we have minus 1. Okay, when x is for example half the view width, we have 2 times the view width divided by 2 times 1 over the view width minus 1 minus 1, 0. When x is 1, the view width, this becomes 2 times the view width divided by the view width minus 1, which is 2 minus 1, which is 1. So this basically is a mapping, so maps 0 view width into -1 1. Okay, now -2 y divided by the view height plus 1. When y is 0, this is 1. When y is the view height divided by 2, this is -2 view height divided by 2 times 1 over the view height plus 1, which is -1 plus 1 is 0. When our y is the view height, well, view height over view height, it will be -2 view height over view height plus 1. -2 plus 1 is -1. So here this is a map, okay, from maps the interval that goes from 0 to view height into what? -1 1, but this mapping right here from 0 to view width -1 plus 1 goes like something like this, like presumably it's a line. It's a line, okay, and this is view width divided by 2. This thing right here with the view, sorry, this is the view height. Okay, let's suppose this is the view height divided by 2. Let's say this is -1. Let's say this is +1. Well, now for 0 we have 1. So it's something like this. It's not the same mapping. It's not the same mapping. The Z, it's just the Z. Okay, so we are just, so this thing right here, okay, is just a mapping, maps, screen space, into normalized device coordinates with the W component set to 0. And this makes much sense because earlier we said that W must be greater than 0. With all So all the math is just the mapping, okay? And like we got it. Why? I don't know. Like, obviously, this is just the transform from screen space to normalized device coordinates. But the projection matrix outputs. It's a transform that outputs points in clip space, which is not for the orthographic projection. I'm feeling like it's working. Like, obviously, it's getting too late to do anything productive. We got it, like we got the basically we now have array from red to blue. We just need to take the difference from the difference vector, the blue position minus the red ball's position. We get our direction vector. Then we can normalize it. And obviously the ray will start from the camera in that direction, and then it's easy because we just have a plane. Okay, so we just need to do the ray plane intersection, and then we get the point on the plane, okay, that we are aiming at. Once we do that, we simply, once we have a target, we say, okay, dude, soldier, follow the like, what's, go, okay, to the target in a straight line, obviously. But, so, this kinda makes sense. I don't know. I can ask ChatGPT. I mean, how does the inverse projection matrix work? Certain matrix that reverse data done by a projection matrix. What a projection matrix does. Projection is used to transfer 3D coordinates into a lower dimensional space. This transformation projects points from a higher dimensional space onto a subspace. Typically, orthographic projection projects points directly along parallel lines onto a plane. Perspective projection projects points such that they appear smaller as they get farther from the viewer. For example, in 3D graphics, a projection matrix enters a 3D column into 2D column on a screen. Inverse projection matrix. The inverse projection matrix is the matrix that, when applied after the projection, can recover or reverse the transformation applied by the projection matrix, of course. However, not all projection matrices have an inverse, because projections are typically non-invertible transformations. Okay, yes. Reducing the dimensionality of space makes sense. They reduce the dimensionality of the data. going from 3D to 2D, since there is a loss of information, one dimension is discarded, the projection is not reversible in the strictest sense. For an invertible projection, one that doesn't collapse dimensions, we can apply an inverse matrix to go back to the original space. For example, if we project from 3D to a 2D plane, you can't perfectly recover the original 3D point because some information has been lost. But in some special cases, the process can be reversed. Types of projections and inverses. Orthogonal projections. In the case of orthogonal projection, the inverse projection can sometimes be constructed if the projection is onto a subspace. Projection onto a 2D plane can sometimes be undone by using knowledge and geometry. The inverse of a perspective projection is much more complicated because perspective projections involve a non-linear transformation. There is no simple matrix inverse that works across all cases because information is lost due to the transformation into lower dimensional space. However, for certain idealized situations or in cameras, or in ideal camera, you can compute a sort of back projection under the assumptions of known parameters, but this often involves complex calculations that may need additional data, camera parameter depth information. Yeah, basically it told me what I already knew. Thank you. So, okay. Now, we went down this rabbit hole without actually understanding here, for example, the W is 1. Here the Z is completely discarded. What the fuck? This is the same as the Stack Overflow thing. Oh my god, the Stack Overflow answer is just this answer. Okay. Oh, note, we do not need to reverse perspective division here because this is array with no intrinsic depth. Other tutorials on Reagan will incorrectly tell you to do this. Ignore the false prophets. We would do that only in the special case of points for certain special effects. Okay, so since this is array with no intrinsic depth, we don't need to use perspective division. Hands off, like, okay, very face value, perspec, yeah, okay, I mean, if you say so, you say so. So we just do that, basically. And once we have these, we just project model view projection inverse. So basically the inverse of the projection, inverse of the view, inverse of the model. Perfect. Everything works. So okay. I'm not very satisfied, but I mean it works. So that's not an issue. Like, I was just curious why, but answers are really lacking in this department. Okay, so now I want oh boy. So this, go away please. Right? Plane? A plane? Like intersect. Do I have a function, or do I have like chat GPT? Right? Intersection with the DirectX toolkit simple math. Yeah. So there is no so array point plus, so this is the parametric, don't want to say bullshit, but this is in the form of point plus direction basically. The plane is in the form normal, so this is the normal dot pro. P is any point on the plane, Q is the point in question, which in case is the array's intersection point. Okay, so we basically take the dot product must be 0, meaning that these two need to be perpendicular. Q is basically a point that is needed to define the plane, because if I just have a normal, if I just have a normal, this plane, this plane, this plane, you have like this plane, this plane, this plane, this plane, this plane, this plane, also this plane, this plane, this plane, this plane. You have an infinite like stack of planes that have the same normal. So you need a point to say belonging to the plane you want. Okay. And the idea is that given here a given here a point, okay, this, so the vector that points from your point on the plane to that point and the normal must be perpendicular. If they are perpendicular, then the point denoted by P is on the plane. If they aren't perpendicular, the point is not on the plane. Okay. So steps to calculate the ray plane intersection. So we need to compute the value of t where the ray intersects the plane. Okay. So P of t would be, so this equation is useful to find all the points, okay, on the ray, on the line, basically. We substitute this in this. Okay, this is our variable here. The normal and the Q are given. Oh, sorry. P is any point on the plane. Yeah. Okay. P minus Q and Q minus P are the same thing. Or better. They're not the same thing, but they have the same direction. So it doesn't really matter here. So to calculate ray plane intersection. So if I take 2 points in space, the vector that goes from the first one to the second one and the vector that goes from the second one to the first one have the same direction. Okay, the only thing that changes is the sign. But they don't have the same direction. They lay on the same like line. Okay, then it's just a matter of like I can get the first vector simply by multiplying the first vector by -1 and vice versa. So by flipping it like by basically flipping it like by flipping it like so. What? Okay, so that's it. Now we just do this, set up the equation. So we need, this gives us the interesting thing about this ray equation is that it gives us a point belonging to the ray just using the parameter t. So we only need to solve for t. So the point on the like, what are the chances there are? What are the scenarios? Either the line, either the ray lies on a plane that has the same normal, so lies on a plane that is parallel to the other one, or it lies on the same on the plane itself. So in this case, the first case, so lies on a plane that is parallel to our interest of our plane of interest, then here no solutions for t. If the two planes are the same, so the ray lies on the plane entirely, infinite solutions. If the ray, in any other scenario, the ray intersects the plane in only one point. So there is only one solution for t. Obviously, what we need to do is to just like, we have our equation, this one, that defines all the points on the ray. We have this equation that tells us whether or not a point is on the plane. We plug the equation we plug our like expression for points, for the set of points on the line in here, and then we solve for t. Okay, here we have dot products, so n dot o plus n dot o minus q. What? N dot o plus n dot so o minus q, n dot o minus q plus t times n dot d. Okay, now we simply minus okay, so some algebra. We isolate our t and then we just need to compute some dot products. Okay, so honestly, I think I'll call it quits tonight. And we got the redirection. So tomorrow we can get the thingy that we want. Have a good night. Bye bye.